So this is module 2 of the course. That is module 2 of 3. After this module now is module 3. So let's have a look at module 2 of the course, CIT333, Software Engineering. So under this module 2 now, we have software development. So I want to start with the definition of software development. Software development can be defined as the set of activities that results in software products. Software development may include research, new development, modification, re-engineering, maintenance, or any other activities that result in software products. Are you getting it now? So the term software development may also refer to computer programming. That is the process of writing and maintaining source code. When we say source code now here, is the set of codes written in a particular language or languages. Are you getting it now? So let's have a look at stages of software development. Number 1, market research. That is, number 1 of the stages of software development is market research. When we say market research now, here, the developer will organize efforts to gather information about markets or customers. It is very important component of business strategy. You know, in any business endeavor, the person will try to make research about market concerning the proposed products. Then number 2, gathering requirements for the proposed business solution. So here now, the software developer will meet customers or prospective customers. He or she will analyze market requirements and features that are in demand. Are you getting it now? Okay. Then number 3, analyzing the problem. Here now, the software developer will make analysis of the problem. The questions to address here include: what input does that project needs? Does the product, that is the software product, does it need names? Does it need numbers? Does it need values? And so on and so forth. Then the developer will ask himself now, what will be the output that is expected of the software? How should the output be displayed? Who should use the software? That is, the expected users of the software. All these questions and more, the developer will ask him or herself. Are you getting it now? So these basic questions will form the guidelines in which the developer will be referring to throughout the stages of the software development. So let's move to number 3. Under stages of software development. Number 3 now. Devising a plan or design for the software-based solution. So here now, the software developer will design a plan of the proposed software project. I will liken this design stage now. I will liken it to somebody who wants to build a house. You know, the architect we first of all draw the plan. So here now, design to software development is analogous to the plan of a proposed building. So here now, or let me say in the plan, where the kitchen will be, where the toilet will be, how the rooms will be arranged, the windows and other things. This is the stage that decision and analysis will be made on them. That is the design stage. So likewise, for software development, in the design stage now, the uh, the manner of the software here now will be analyzed and decided. Are you getting it now? Okay. So let's move to number 3. Implementation or coding of the software. So when we say implementation now, design has been gotten. That is how the software project will be. This is how the data will be arranged. This is the output. This is how it will be. The interface, this is how it will be. All those ones have been done in the design stage. So when it gets to number 5 now, the implementation or coding of the software, here now the design is just transformed into lines of codes. The design will be transformed to lines of code. Are you getting it now? I hope you are jotting things down. So let's move to number 6 now, testing of the software. Before any software can be delivered, that software must be tested. That software must be tested. The software domain will be tested for bugs, that is for different errors. Are you getting it now? And we have different sets of tools available for software testers and developers to detect and fix defects in the software. So here, the software will be tested to know how far it is accurate. Are you getting it now? Then the next one is deployment. Here now, the software is ready now to be deployed to the expected users. So the general development process consists of several interrelated activities with possible transitions between them. So these activities can occur at the producer site or at the consumer site or both. Are you getting it now? Then the last one, maintenance and bug fixing. Maintenance and bug fixing. Here now, at this stage, when the product is updated to meet changing needs and environments, fixing undetected bugs during testing stage and defects might arise during updates. What is there is that under this maintenance and bug fixing now, the software will be maintained. It's like somebody who has built a house, let's say 5 years ago. Then there is a new material now outside. Maybe the house before, the person used the louver windows, but now the person may want to change it to another modernized window type. Then at this stage now, we say that the person is making maintenance to his or her house, or maybe there is any fault on the house. Maybe there is a roofing leakage, or maybe there is scratch on the wall. So at this stage now, the owner will make a maintenance. Likewise, when it comes to software, as new hardware equipment, as we get them, then there is need to update the existing software in order to be compatible with the latest hardware equipment. Are you getting it now? Then during testing, it might be that some bugs they were not detected. So at the maintenance stage now, there will be fixing of those bugs. That is, when we say bugs, errors. There will be fixing of those errors at the maintenance and bug fixing stage. Are you getting it now? Okay. So let's have a look at Unit 2. Software development life cycle models. Software development life cycle models. So when we say model, that is a particular method that a developer can use to develop a software project. So let me give the definition now in short. Software life cycle model describe the phases of the software cycle and the order in which these phases are executed. We have a lot of models. So many companies they adopt their own, but all are very similar patterns. All are very similar patterns. So let's look at some existing models now. That is software development life cycle model. Number one, the general model. General model. That's number one. The general model. For this general model now, is going to start from requirement to design to implementation and to testing. That is, for this general model now, it has 4 phases. It has 4 phases. Phase 1 is the requirement. Phase 2 is the design. Phase 3 is the implementation or coding. And the last phase, testing. So for general model, each phase produces deliverables needed by the next phase in the life cycle. When we say deliverables here now, that is the end product, which means requirement phase we produce the end product, or let me say the raw, it will now become the raw product that design phase we use. When design phase is completed now, then it will produce the raw material, that is the end product that implementation will use. When implementation phase is completed, then the deliverable of implementation or coding phase now will now be for that of a testing phase. Are you getting it now? So for the general model now, phases overlap. Phases overlap. That is, The second stage starts before the completion of the first stage. The second stage starts before the completion of the first stage. Don't be confused that for general model, each phase produces deliverables needed by the next phase. What is meant there is that what design phase we need will be produced by requirement phase, and what implementation phase we need will be produced by design phase, and what testing phase we need will be produced by implementation phase. I think you understand now. Okay, so let's move to number 2. So for number 2, waterfall model. Waterfall model. Are you with me now? Don't forget that we started with number 1, the general model, where the deliverables needed by the next phase are produced by the previous phases. Are you getting it now? Or by the previous phase. Then for general model, the previous phase now will be converted to the next phase. That is, requirement will be converted to design, design will be converted to implementation, implementation will be converted to testing. I think you get it now. So let's have a look at waterfall model. Number 2, waterfall model. For waterfall model now, this is the most common life cycle model. It is also referred to as a linear sequential life cycle model. This model is very simple to understand and use. In waterfall model, each phase must be completed before the next phase can begin. You know, that is the key difference between waterfall model and general model. For general model now, phases overlap, but for waterfall model, phases don't overlap. For waterfall model, previous phase must be completed before the next phase. Are you getting it now? So at the end of each phase, there is always a review to ascertain if the project is in the right direction or whether or not to carry on or abandon the project. So unlike the general model now, as I've said, phases do not overlap in waterfall model. Are you getting it now? So let's see some advantages of a waterfall model. Number 1, simple and easy to use. Number 2, it is easy to manage due to the rigidity of the model. That is, each phase has specific deliverables and a review process. Then number 3, phases are processed and completed one at a time. That is for waterfall model. Phases are processed and completed one at a time. Then the fourth advantage now of a waterfall life model is that it works well for smaller projects where requirements are very well understood. I think you have known the advantages of a waterfall life cycle model. So let's consider the disadvantages of a waterfall life cycle model. For the disadvantages now, adjusting scope during the life cycle can kill the project because the project for waterfall is rigid. So Making adjustments now can kill the project. Then number 2 disadvantage, no working software is produced until the last life cycle. That is, there will be no software produced until late during the life cycle. That is, it's going to take time. It's going to take time. Then high amounts of risk and uncertainty. High amounts of risk and uncertainty surround waterfall life cycle model. Then number 4, poor model for complex and object-oriented projects. So if you are using a waterfall model for complex and object-oriented projects, then the software will be less performing. It will be poor. Are you getting it now? Then it's a poor model for long and ongoing projects. It is also poor model where requirements are at a moderate to high risk of changing. So those are the disadvantages of a waterfall life cycle model. So we are moving to number 3 now. We are moving to number 3. V-shaped model. V-shaped model. So for V-shaped model now, just like the waterfall model, the V-shaped model life cycle is a sequential part of execution of processes. That is, V-shaped model is sequential in part of execution of processes like waterfall model we just considered. Are you getting it now? So in V-shaped model, each phase must be completed before the next phase begins. So like waterfall model now, for V-shaped model, each phase must be completed before the next phase can begin. Then testing is emphasized in V-shaped model. Testing is emphasized in V-shaped model. Are you getting it now? Okay. So let's continue now. The testing procedures are developed early in the life cycle before any coding is done at all. Before any coding is done at all in V-shaped model, the testing procedures must have been developed in the early life cycle. Are you getting it now? Then requirements begin the life cycle model just like the waterfall. So the first phase of a V-shaped model is requirements. Are you getting it now? Like a waterfall model. Are you getting it? Okay. Here now, that is concerning this requirements now, that is that requirements must start in V-shaped model. A system test plan is created, that is before development in V-shaped model. A system test plan is created. The test plan will focus on meeting the functionality specified in the requirements gathering. So when we get to requirements in the course of the lecture, you will understand better the meaning of requirements. Then under V-shaped model, the high-level design phase focuses on system architecture and design. So an integration test plan is created, as I've said, in this phase as well in order to test the pieces of the software systems ability to work together. That is, the pieces of the software system, the ability to work together, that is, to work in compatibility, will be tested. Are you getting it now? Okay. Then the low level design phase is where the actual development components are designed and unit tests are created in this phase as well. So are you getting it now? So let's do the summary of the advantages of a V-shaped model. It is simple and easy to use. Each phase has specific deliverables. Number 3, higher chance of success over the waterfall model due to the development of test plans early on during the life cycle. That is, development test plans have been created early on during the life cycle. Are you getting it now? Then number 4, it works well for small projects where requirements are easily understood. So let's consider the advantages of the disadvantages. We have considered the advantages, right? So let's have a look at the disadvantages of a V-shaped model. It is very rigid, like the waterfall model. So here now, V-shaped model is very rigid. When we say rigidity, that is not easy to adjust. Adjust the meaning of that rigidity. Not easy to adjust like a waterfall model. Then number 2, little flexibility and adjustment are difficult and expensive. You know, it is rigid. So any little adjustment now made will be difficult and expensive. Are you getting it now? Then number 3, the software is developed during the implementation phase. So no early prototypes of the software are produced. So it's only at the implementation phase that the software is developed. Then number 4, the model doesn't provide a clear path for problems discovered during testing phases. For V-shaped model, it doesn't provide a clear path for problems discovered during testing phases. That is, some problems that were discovered during the testing phases, the model will not provide a clear path for them. Are you getting it now? Okay. So we want to have a look at the fourth model. The fourth model. And this one is called the incremental model. Incremental model. So let me open another page. Incremental model. That's number. So number 4 now. Incremental model. Incremental model. When we say incremental model, it's just an intuitive approach to the waterfall model. An intuitive approach to the waterfall model. That is, incremental model is like a multi-waterfall model. Multi, that is many waterfall model. That is multi-waterfall model. Are you getting it now? So for incremental model, circles are broken into smaller, more easily managed iterations. That is, circles are broken to smaller and more easily managed iterations. When we say iterations here now, we mean repetitions, or let me say sub-circles. For incremental model, circles, that is, each circle is broken to sub-circles. Are you getting it now? So each of the iterations goes through the requirements, design, implementation, and testing phases. So what happens here is that for incremental model, it will be possible to have working software early on during the software life cycle. So during the software life cycle now, we can get a working software. Are you getting it now? So that's just about incremental model. Are you getting it now? So let's have a look at the advantages of incremental model. For incremental model now, one, it generates working software, as I've said, quickly and early during the software life cycle. So during the software life cycle, a working software is already generated for incremental life cycle model. Then there is more flexibility. There is more flexibility for incremental model. That is, incremental model is not rigid as a waterfall or V-shaped. So it is flexible. Are you getting it now? So it will be inexpensive now to make adjustments to scope and requirements, because it is not rigid. So it will be very easy to make adjustments to requirements of incremental model. Then number 3, it is easy to test and debug during a smaller iteration. You know, each circle now is broken to iterations, so it will be easy to test and fix errors on this type of model. Are you getting it now? Then number 4 now, it is easy to manage risk. It is easy to manage risk because risky pieces are identified and handled during its iteration. So it's during iteration now, that is a smaller units of or smaller divisions of each circle. So it will be easy to manage the risk. Are you getting it now? So it is easy to manage a landmark on the iterations. That is, each of the iterations now is an easily managed landmark. When we say this issue of iteration now, it is just like small. It will be small segments, small parts of a circle. You understand now? So it will be easy to make any management we want to make on it. So let's have a look at the disadvantages of incremental model. For incremental model disadvantage, each phase of an iteration is rigid and do not overlap each other. Are you getting it now? Then problems in system architecture may arise as a result of the inability to gather requirements up front for the entire software life cycle. I think you can get the disadvantages now. Each face of an iteration is rigid. I want you to get that one clear. Each face of the iteration is rigid and they do not overlap each other. They do not overlap in the sense that the first must be completed before the start of the second. The second must be completed before the start of the third, and so on and so forth. Are you getting it now? Okay. So we are moving to number 5, spiral model. Spiral model. When we say spiral model now, it is similar to the incremental model. It is similar to the incremental model and with more emphasis placed on risk analysis. The spiral model has 4 phases and they are planning, risk analysis, engineering and evaluation. Let me come again. Planning, risk analysis, engineering and evaluation. Here now, a software project continually goes through these phases in iterations which are called spirals. In the baseline spiral, requirements are gathered and risk is assessed. Each subsequent spiral builds on the baseline spiral. So, each of the subsequent spirals will build on the baseline spiral. Are you getting it now? Then, requirements are gathered during the planning stage. So, it is the planning stage that you will gather the requirements. Then, in the risk analysis phase now, a process is carried out to discover risk and alternate solutions. That is the solution that can be provided. Are you getting it now? So a prototype is produced at the end of the risk analysis phase. A prototype is produced at the end of the risk analysis phase. Don't forget that spiral model has 4 phases and they are planning phase, risk analysis phase, engineering phase and evaluation phase. Are you getting it now? Okay. Software is produced in the engineering phase. Are you following now? Requirements are gathered during the planning phase. Are you with me now? Then the software is produced during the engineering phase alongside with testing at the end of the phase. Then the evaluation phase provides the customer with opportunity to evaluate the output of the project to date before the project continues to the next spiral. So before the project continue to the next spiral now, the evaluation phase will make provision for the customer opportunity to evaluate the output of the project to date. Are you getting it? Okay. Then in the spiral model, the angular components denote progress. The angular component of the spiral model denotes progress and the radius of the spiral denotes cost. So like the spiral now, let me make a sketch of it here. I'm coming. I think you can see the sketch now. I think you can see the sketch. The angular component denotes progress. That is, you can see the angular component It's like physics. When we say angular velocity, see my hand. So that is the angular component. Angular component. It denotes progress, and the radius of the spiral denotes cost. So you know this is the center of the spiral. From here to here is the radius. Then from here to here is the radius. So the radius now denotes cost. Are you getting it now? So don't forget, spiral model has 4 phases: planning, risk analysis, engineering, and evaluation. Planning, risk analysis, engineering, and evaluation. Are you getting it now? Okay, so let's have a look at the advantages of a spiral model. For spiral model, high amount of risk analysis. High amount of risk analysis. Then it is good for large and mission critical projects. I will explain that number 2. Large and mission critical projects. So spiral model is good for large and mission critical projects. When we say mission critical project, that is the mission, the project we accomplish is somehow critical. That is, it's not a mission that can fail. When we say critical here now, it's not a mission that can fail. Are you getting it now? Okay. For instance now, mission critical project, let's say military software now. You know, military mission is critical. That is, it's not a mission that must fail. It's not a mission that must miss a target. So this type of model now can be used to create a military software. Are you getting it now? Because military operation is a mission critical. The mission must not be missed, or the target must not be missed. Are you getting it now? Okay. Then the software is produced early in the software life cycle. So early in the software life cycle, the software is already produced. So let's look at the disadvantages now. Number 1, it can be a costly model to use. Risk analysis requires high specific expertise. So to do the analysis of the risk, it needs highly specific expertise. Are you getting it now? Then project success is highly dependent on the risk analysis phase. Then it doesn't work well for smaller projects. So you don't need spiral model for small projects. That is, for small mission, you don't need a spiral life cycle model. So spiral life cycle model is needed for big or large projects. Are you getting it now? So it will not work well for smaller projects. So let me come again for the disadvantages now of a spiral life model. It can be a costly model to use. Then risk analysis requires highly specific expertise. Then project success, that is success of the project, is highly dependent on the risk analysis phase. So at the risk analysis phase now, it must be done with high expertise, because The success of the project depends majorly and highly on the risk analysis phase. Are you getting it now? So it doesn't work well for smaller projects. So I think you have gotten the different life cycle models for software development. We have the general model, the waterfall model, the V-shaped model, the incremental model, and the spiral model we just discussed now. So I think you have gotten one thing or the other. So we are moving to the next unit now, which is a requirements phase. Requirement phase now. Requirements phase. So let's have a look at it. So this is requirements phase now. So when we say requirement phase, we have just considered models. The one we just considered, they were models. But we want to consider phases now in software development life cycle. So requirement phase. For requirement phase, business requirements are gathered in this phase. This phase is the main center of attention of the project managers and stakeholders. That is, the project managers and stakeholders, they pay major attention on this phase. Are you getting it now? So they will be having meetings with the managers, that is the developers, the software developers. They will be having meetings with the managers, with the stakeholders, and users. Are you getting it now? In order to determine the requirements expected of the proposed software project. Are you getting it now? So the general questions that require answers during a requirement gathering phase are, that is, at this requirement phase, some questions are placed and the answers must be given. Are you getting it now? So the questions include: who is going to use the system? How will the people use the system? What data should be input into the system? And what data should be output by the system? Are you getting it now? So here, these and more other questions will be produced and answers provided. Are you getting it now? So, moreover, at this requirement phase now, a list of functionality that the system should provide, which describes functions the system should perform, business logic that processes data, what data is stored and used by the system, and how the user interface should work, is produced at this point. When we say user interface, it just means how the computer will present output to the user. Are you getting it now? That is why we say graphic user interface. Graphic user interface. So I think you get the meaning of a user interface now. The requirements development phase may have been preceded by feasibility study. So before the requirement phase now is carried out, feasibility study must have been done. That is, when we say feasibility study now, that is, study that is workable. That is, when we say feasibility, it means workability. Are you getting it now? Okay. So the requirement phase may be divided into requirement elicitation. That is, when we say requirement elicitation, it means gathering the requirements from stakeholders. Are you getting it now? That is, under requirement elicitation, the requirements will be gathered, will be obtained, let me use that word, from stakeholders. Are you getting it now? Then there will be analysis. There will be analysis. After elicitation, there will be analysis. So analysis here means checking for consistency and completeness. That is, the consistency and completeness of the project will be checked here. Are you getting it now? Then it will be followed by requirement specification. Don't forget, requirement phase can be divided into requirement elicitation, requirement analysis, requirement specification. So under requirement specification now, there will be documentation of the requirements. That is, the gathered requirements will be documented, will be recorded. I think you are getting it now. Okay. Then there is also requirement validation. Requirement validation. We are still going to discuss each. So I'm just naming them now. So requirement validation. So requirement validation means making sure that the specified requirements are correct. That is, here now, the specified and gathered requirements are verified correct. Do you get it now? Okay. So let's have a look at types of requirements. Types of requirements. Requirements can be categorized as follows. 1. Functional requirements. Functional requirements. When we say functional requirements, they describe the functionality that the system is to execute. For example now, formatting some text or modulating a signal. When we say modulating a signal, that one has to do with a network issue. Network issue. That is, maybe analog signal is converted to digital signal and vice versa. Are you getting it now? So, number 1 of types of requirements is functional requirements. Functional requirements. Are you getting it now? Okay. Then 2, non-functional requirements. Non-functional requirements. So for non-functional requirements, they are the requirements that act to constrain the solution. These requirements, that is non-functional requirements, they will act in order to constrain the solution. Are you getting it now? Non-functional requirements are sometimes known as quality requirements or constraint requirements. That is, it is the non-functional requirements that determine the quality, or let me say that makes the quality of the system. Are you with me now? So they are also called quality requirements or constraint requirements. Are you with me now? Okay. So no matter how the problem is solved, that is, the problem the software is designed to solve, no matter how the system solves the problem now, constraint requirements must be adhered to. That is, constraint here means regulations. Constraint here means regulations. Are you getting it now? So take it. Constraint here means regulation. That is, the working of the system, that is, the software project, must be regulated, must be put to constraint. Do you get it now? Okay. So we want to go further now. Okay. Consider this addition now. You know, it is important to note that functional requirements can be directly implemented in software. That is, during the software development, functional requirements are directly implemented, but the non-functional requirements are controlled by other aspects of the system. Okay, for example now, in a computer system, reliability is related to hardware failure rates. Reliability is related to hardware failure rate. That is, the hardware of the system, the rate the rate the hardware fails will determine how reliable the hardware is. Are you getting it now? Then performance is controlled by CPU and memory. That is, performance of a system is controlled by the central processing unit and the memory, especially the RAM, that is random access memory. Are you getting it now? Non-functional requirements can in some cases be broken to functional requirements for software. Let me explain this now. For example, a system level non-functional safety requirement can be decomposed. You see, it's a non-functional safety requirement now. It can be decomposed into one or more functional requirements. Are you getting it now? Then, in addition, a non-functional requirement may be converted into a process requirement when the requirement is not easily measurable. Okay, let me give example to this now. A system level maintainability requirement may be decomposed into restrictions on software constructs or limits on lines of code. So by now, I think you get the explanations on the types of requirements, which are functional requirements and non-functional requirements. Don't forget that functional requirements is also known as, or let me say, functional requirements now, they are also called quality requirements or constraint requirements. That is, requirements that set regulations. Are you getting it now? So that's all about functional and non-functional requirements. So we want to proceed to requirement analysis. That is, analysis on requirements. So when we say requirement analysis in software engineering or other systems engineering, requirement analysis consists of those activities that go into determine the needs or conditions to meet for a new or altered product, taking account of the possibly conflicting requirements of the various stakeholders such as beneficiaries or users. Are you getting it now? So, requirement analysis is critical to the success of a development project. That is, when you are developing a project, requirement analysis is important. Requirements must be actionable, it must be measurable, and it must be testable. Are you getting it now? So, we are going to consider why is it necessary to carry out requirement analysis. That is, the need for requirements analysis. The needs for requirement analysis. Studies reveal that insufficient attention to software requirements analysis at the beginning of a project is the major reason for critically weak or failed projects. Are you getting it now? Okay, let me liken this issue of requirement analysis now. Let me liken it to a building. You know, when a building is to be built now, the requirements expected of the building must be analyzed in detail, must be analyzed. That is, emphasis must be laid on the analysis of the requirement. That is, the toilet, how is it going to be? The kitchen, how is it going to be? The windows, how are they going to be arranged? Or let me say, how many windows, how many can a particular room has? Or maybe the sitting room, how many windows can it has? And so on and so forth. So the requirements now, that is, what is required of the house to produce at the end of the completion must be critically analyzed. So also for a software project, the requirement must be analyzed at the beginning of the project, because if the requirements are not critically analyzed, then the project will become a weak one, even a failed one, because it will be difficult now for the project to fulfill the basic task for which the project is designed for. So that is the reason why there is need for requirement analysis. Are you getting it now? So let's have a look at requirement analysis process. So as we have considered need for requirement analysis now, so let's talk about requirement analysis process itself. So when we say requirement analysis now, it is the process of understanding the client needs, that is, user needs and expectations from the proposed system. It is a well-defined stage in the software development life cycle model. That is, requirement analysis, or let me say simply requirement, is a well-defined stage in the software development life cycle Requirements are a description of how a system should behave. In other words, a description of system properties or attributes. Okay. Considering numerous levels of dealings between users, business processes, and devices in worldwide companies today. That is, we have numerous dealings between users, business processes, and the devices. When we say devices now, that is the hardware devices in different companies of the world. So there are immediate and composite requirements from a single application from different levels within an organization and outside it. The software requirements analysis process involves the complex task of eliciting and documenting the requirements of all customers. So when you are performing requirement analysis now, complex task of eliciting and documenting requirements from users or from clients. Are you getting it now? Then modeling and analyzing these requirements and documenting them as a foundation for system design. So you are going to model these requirements, you are going to analyze them, and you are going to document them as a foundation for the system design. Are you getting it now? So the job of requirement analysis is dedicated to a specialized requirement analyst. That is, a requirement analyst now is dedicated of the job of a requirement analysis process. Are you getting it now? So the requirement analysis function may also come under the scope of project manager, program manager, or business analyst, depending on the hierarchy of the organization. Are you getting it now? So what we have been saying is that requirement analysis is very important in the development of a software system, because if this requirement analysis phase, if it's not properly done, then the expected workability of the system is going to be affected. Are you getting it now? Okay. So we want to have a look at the steps in carrying out requirements analysis process. We want to look at the steps. 1. Fix system boundaries. Fix system boundaries. So this is the initial step which helps in identifying how the new application fits in to the business processes, how it fits into the larger pictures, as well as its capacity and limitation. That is the capacity of the system and its limitation. That is why we call it system boundaries. System boundaries. That is the extent the system can work and the capacity of the system. Then 2, identify the customer. Here now, we focus on identifying who the users or customers of the system will be. That is to say, we know the group of people who will be either directly or indirectly impacted by the new system. The new system we are planning. Those people that will be either directly or indirectly impacted by it. Are you getting it now? So this will allow the requirement analyst to know in advance where he has to look for answers. That is, the requirement analyst now will know before where he will look for answers. That is, answers to the various requirements posed before him or her. Are you getting it now? Okay. So we are moving to the next branch of requirement phase of software development, and this is a requirement elicitation. As I've mentioned before, when we say requirement elicitation now, here now, the requirements expected of the proposed system now will be obtained. That is elicitation here now, to obtain them from the stakeholders or from the users or from the group of people that want to use the system. Are you getting it now? So here now, we are going to take into account the multiple stakeholders involved. The list of requirements gathered in this manner could go into pages. That is, as we are documenting the requirements gathered under requirements elicitation now, it can be written running to pages. The level of detail of the requirement depends on the number and size of user groups. That is, the more the people that will use the project, then the more will be the details of the requirements. Are you getting it now? Then the level of the detail of the requirements, that is, the requirement list detail now, also depend on the degree of complexity of the business processes and the size of the application. You know, it depends on the number of people, that is the level of detail of the requirements now. The detailed requirement level, let me say it like that, depends on the number of people that will use the system, and it also depends on the degree of complexity of business processes and the size of the application. So let's have a look at the problem faced in requirement elicitation, that is, in obtaining requirements. The requirement analyst, they face some problems. They are ambiguous understanding of processes, inconsistency within a single process by multiple users, insufficient input from stakeholders, conflicting stakeholder interests, Changes in requirements after project has begun. So let me have a small explanation on the 5 problems here now. Number 1, ambiguous understanding of processes. That is, the understanding of the processes will be somehow ambiguous. That is, will be somehow unclear to the requirement analyst. Then there will be inconsistency within a single process by multiple users. Let's say there is a particular process now. The software will perform. Are you getting it now? The process is single, but users are multiple. So there will be generation of inconsistency. Even it may result to process conflict. Are you getting it now? Okay. Insufficient input from stakeholders. Maybe the project now is supposed to be at a cost of $1,000, and the client can manage to pay $800. Then the cost now is insufficient, and when the cost is insufficient now, there will be problem concerning the requirements the client is expected of the system. It's like somebody needs a house now. The person can manage to pay 2 million naira, and the requirements the person needs from the house now, that is the requirements the person is expecting from the house after completion now, let's say we cost 2.5 million. So there will be problem in fulfilling the requirements when the owner can only afford 2 million naira. So there will be problem when it comes to the fulfillment of the requirements in full. Are you getting it now? Then conflicting stakeholders' interest. Here now, the stakeholders, their interest may be conflicting. Let's say a particular stakeholder wants the system to do this, then another stakeholder wants the system to do that. And if the two interests now, if they are going to be implemented in the software, the two interests may be conflicting with each other. Are you getting it now? So here now, there will be problem. There will be problem to requirements here. Then changes in requirements after project has begun. So the project has started already. The project is in progress, and one of the user just come and indicate a change in the already accepted and implemented requirement. Then there will be problem. It's like somebody building house now. The bricklayers and other workers, they have started building the house. maybe the house is getting to the roofing stage now, and the owner just come and say, I want the size of the kitchen to be this. That is, the size of the kitchen now is now being changed from the original size that has been implemented. So there will be problem to requirement elicitation here now. So that's just it. Then let's have a look at tools used in requirement elicitation. We have some tools, that is some instruments used to obtain requirements. Are you getting it now? So the tools include stakeholder interviews, that is, series of interviews will have been conducted for the stakeholders. Are you getting it now? So requirements elicitation include stakeholders interviews and focus group studies. Then let's consider other tools that can be used for requirement elicitation. Flowcharting of business processes can be used. Then use of the existing documentation like user manuals, organizational charts, process models, and systems or process specifications. All this and more, they are tools used in requirement elicitation. Are you getting it now? Then, moreover, on-site analysis can also be used as a requirement elicitation. Then interviews with end users, market research, and competitor analysis, they are also used in making a requirement elicitation. So are you getting it now? Okay. But we have modern tools. We have modern tools that are better equipped to handle the complex and multi-layered processes. Are you getting it now? Okay, so we have modern tools that are better equipped to handle the complex and multi-layered process of requirement elicitation. So let's have a look at some of the current tools now for requirement elicitation. 1. Prototypes. 2. Data flow diagrams, DFD. Data flow diagrams. 3. Transition process diagrams, and many others. Are you getting it now? So let's have a look at requirement analysis, although we have discussed it, but let's review it. The moment all stakeholder requirements have been gathered, a structured analysis of this can be done after modeling the requirements. Some of the software requirement analysis techniques used are requirements animation, automated reasoning, knowledge-based critiquing, consistency checking, analogical and case-based reasoning. I think you get some of the software requirements analysis techniques used now. Let me name them again. We have requirements animation. We have knowledge-based critiquing. Then we have automated reasoning. consistency checking. Then we have analogical and case-based reasoning. Do you get it now? So let's have a look at requirements specifications. Requirement specification. So as I said, requirement specification means requirement features. Are you getting it now? So after requirements have been obtained, modeled, and analyzed, they should be documented. They should be documented. And when the documentation is to be done, it must be clear and definite. That is, it must be in clear and definite terms. A written requirements document is crucial, and as such, its circulation should be among all stakeholders, including the client, the user groups, the development teams, and the testing teams. So, a written document must circulate among all these people mentioned. Are you getting it now? Then, it has been observed that a well-designed, clearly documented requirement specification is vital and serve as a one base for validating the stated requirements and resolving stakeholder conflict. That is, if there is any conflict, a well-designed and clearly documented requirement will be the base for validating the stated requirements and to resolve stakeholder conflicts. It will also be a contract, that is, it will serve as a contract between the client and the development team. Then, it will also serve as a basis for system design for the development team. Are you getting it now? Okay. Moreover, it will serve as a benchmark for project managers for planning project development life cycle and goals. It will also serve as a source for formulating test plans for quality assurance and testing team. Quality assurance and testing teams. It will also serve as a resource for requirement management and requirement tracing. Then it will also serve as a basis for evolving requirements over the project lifespan. So, have you gotten it now? That a clearly and well documented requirement specification will serve as all those functions mentioned. So that is about requirements specification. That is all about requirement specification. So summarily now, software requirement specification is a document that lists out stakeholders' needs and communicate this, that is, these needs to the technical community that will design and build the system. Then, software requirement specification involves scoping the requirements so that it meets the customer's vision. Are you getting it now? Then, software requirements specification serves as a starting point for software, hardware, and database design. Software requirement specification describe the function, that is, functional and non-functional specifications of the system Are you getting it now? Performance of the system and the operational and user interface constraints that will be governed. That is, that we govern the system development. So to overcome problems arising from software requirement specification. Requirement specifications may be documented separately as this now. One, user requirements. That is, document the requirement specification. Document it as user requirements. Two, document it as system requirements. Do you get it now? So if you are documenting it as a user requirements, it will be written clear in precise language with plain text and use cases for the benefit of the customer and end user. Then, if you are documenting it as system requirements, it will be expressed as a programming or mathematical model meant to address the application development team. Are you getting it now? So we are going to look at requirements management. So when we say requirement management now, it's just all the inclusive process that includes all aspects of software requirements analysis and as well ensures verification, validation and traceability of requirements. Effective requirements management practices assure that all system requirements are stated without any error. That is, all the system requirements, they must be stated without any error. Omission and errors are corrected if there are any, and that evolving specifications can be included later in the project life cycle. So it must be free of errors. Then if there is a omission and if there is a error, then they are corrected. I think you get it now. So we are going to move to the next phase of software life cycle development. We have considered the first phase, requirement phase. So we are moving to the second phase now, called design phase. So when we say design phase, as I've said, it can be likened to the plan of a proposed building. Like that is a technical drawing by an architect for a proposed building. The software system design is formed from this result of the requirement phase. That is, the requirements gathered. Now, we now determine how the design will be. It's like somebody who wants to build house. The requirements, the owner of the house is expected of the house. We now determine how the architect will draw the plan of that house. Are you getting it now? The deliverables in this phase include hardware and software and communication and software design. Are you getting it now? So we are going to go deep now on this second phase called design phase. So let me define what a software design phase is. A software design phase, now, as I've said, or let me simply say, a project design is a meaningful engineering representation of some software product that is to be built. A design can be traced to the customer's requirements. That is, design is produced from the requirements obtained from the customers, and it can be assessed for quality against predefined criteria. So in the software engineering context now, design focuses on 4 major areas of concern. That is, when we are dealing with software design in software engineering projects, the design will focus on 4 major areas, which are data components, architecture components, interfaces components, and the component itself. Are you following now? Or let me put it like this. Data. The component here means division. You understand now? So, data, that is the data type to be used. Architecture, the interfaces, that is how the system will produce the output to the user. Then components itself. Are you getting it now? So the design process is very important. The design process is very important. I want you to take note of that. Let me tell you, we are still going to explain on the 4 major areas of concern one by one. We are going to talk about the data design. We are going to talk about architectural design. We are going to talk about interface design, and we are going to talk about component design. Are you following now? So the design process is very important. It's very important. For instance now, as a laborer, one will not attempt to build a house without an approved blueprint. That is, without an approved plan. Are you getting it now? Because this will pose risk to the structural integrity and customer satisfaction. So if the laborer now avoid the approved blueprint, then there will be a risk to the structural integrity of the house and to the customer satisfaction. So likewise, the approach to building a software, that is the approach to develop a software project is not different, as I've been maintaining. You understand now? The emphasis in design is on quality. Are you getting it now? The emphasis on design is on quality. It is important to note that this is the only phase in which the customer's requirement can be precisely translated into a finished software product or system. That is, this is the let me say the only hope phase for the customer requirements to be translated to his or her intended desire. Are you getting it now? So during the design process, the software specifications are changed into design models that express the details of the data structures, system architecture, interface, and components, as I've mentioned. Are you getting it now? So each design product is re-examined. You are going to re-examine each design product for quality before you move to the next phase of the software development. Are you following now? So we are going to have further discussion of the 4 major areas of concern when we are dealing with software design. Let me repeat. They are data design, architectural design, interface design, and component design. So let's have a look at data design. When we say data design now, when we say data design, here now, the data design created by changing the analysis information model. That is, you are going to change the analysis information model now into data structures needed to implement the software. Part of the data design may occur in combination with the design of the software architecture. More detailed design occurs as each software component is designed. Note that more detailed data design occurs as each software component is designed. That is, under this data design now, the structure of the data is also one course. Data is also one course. Data structure. The structure of the data now will be determined. Are you getting it now? So for number 2, architectural design. For architectural design now, it defines the relationship among the major structural elements of the software. The design pattern can be used to attain the requirements that have been defined for the system and the constraints that affect the way in which the architectural patterns can be applied. It is derived from the system specification, the analysis model, and the subsystem interactions defined in the analysis model. Are you getting it now? So let's have a look at architectural. No, we have dealt with architectural design. So we are moving to number 3, interface design. As I've said now, when we say interface, this has to do with how the computer will present information to the user on the screen, especially. So interface design will explain how the software elements communicate with each other. with other systems and with human users. Are you getting it now? So much of the necessary information required is provided by the data flow and control flow diagrams. Are you getting it now? So interface design, when we say interface, it has to do with between. Inter means between, that is more than one. Are you getting it now? That is how the software elements in the software project, how they will communicate with each other. When we go further into modules, you understand better, and you will know that the software elements, they communicate with each other. A software element in module 1 can communicate with a software element in module 3, and so on and so forth. So how the software elements, how they communicate with each other, how the software elements, how they communicate with other systems, and how the software elements, how they communicate with human users. All these are referred to as interface design. You know, I said how the information will be presented to the user now, that is the user of the software. Are you getting it now? So let's have a look at the fourth one, component level design. Component level design. So when we say component level now, here now, the component level design will convert the structural elements defined by the software architecture, that is the structural elements defined by the software architecture now, will be converted into procedural descriptions of software components using information acquired from the process specification. Are you getting it now? Then from the control specification and state transition diagram. Do you get how the component level design now, how it is? It is this part that will convert the structural elements defined by the software architecture into procedural descriptions of software components by using information acquired from process specification, from control specification, and from a state transition diagram. Are you getting it now? Okay. So let's have a look at design guidelines. Design guidelines or rules. You can say design guidelines or design rules. So in order to assess the quality of a design, then there is yardstick. There is yardstick for a good design. So the yardstick now should be established to make the design possess the following. 1. Exhibit good architectural structure. Be modular. 2. Contain distinct representations of data, architecture, interfaces, and components. That is, components means here now modules. When you get to modules, you understand better. Then 3. Lead to data structures that are appropriate for the projects to be implemented and be drawn from recognizable design patterns. Then 4, be modular. Are you getting it now? It's like I've mentioned that be modular before. Then lead to components that exhibit independent functional characteristics. 6, lead to interfaces that reduce the complexity of connections between modules and with external environments. Then be derived using reputable method that is driven by information obtained during software requirements analysis. So all these criteria, they are not acquired by chance. You understand now? So the software design process promotes good design through application of fundamental design principles, systematic methodology, and through review. So all that I've stated now, they are design guidelines, that is design rules that will enable the developer to get a good and reputable software project. So we want to look at design principles briefly. Design principles. Number 1, the design process is a series of steps that allow the designer to describe all aspects of the software to be built. However, it is not merely a recipe book, but a competent and successful design. The design must use creative skill, past experience. That is, the designer now must use creative skill. He or she must use past experience. He or she must use a sense of what makes good software and have a committed to quality. So that is one of the principles of design, that is software design. Are you getting it now? The set of principles which has been established to help the software engineer in directing the design processes are: the design process should not suffer from tunnel vision. I want you to consider that principle. The design process should not suffer from tunnel vision. Then the design should be traceable to the analysis model. The design should not reinvent the wheel. To reinvent the wheel means to be going back. The design must not be the one that will be taking the work back. Are you getting it now? The design should reduce intellectual distance between the software and the problem. The design should show uniformity and integration. The design should be structured to degrade gently, even with bad data or bad events. The design should be reviewed to minimize conceptual errors. When we say conceptual error, that is semantic errors. And when we say semantic errors, that is error that has to do with a meaning. You understand now? Semantic, that has to do with a meaning. Then design is not coding, and coding is not design. I want you to know that. Design is not coding, and coding is not design. So when you are doing design phase, you are not coding, and when you are doing coding phase, you are not designing. Are you getting it now? The design should be structured to accommodate change. In future, there may be change to the software. Then the design must have been made in order to accommodate any future change. It's like a house built. The house must be built. Maybe in future, the owner want to make adjustments. Maybe the owner want to turn the bedroom to kitchen, or maybe the owner want to convert 2 rooms to a sitting room. So the design of the house must be done in order to accommodate such future adjustments. Are you getting now? So likewise, the design of a software must be made in order to accommodate any future adjustments. So those are the principles governing design phase of a software. So we want to have a look at a fundamental software design concept. So when you say concept here now, idea. Over the past 4 decades now, a set of fundamental design concepts has evolved, each providing the software engineer with a foundation from which more sophisticated design methods can be applied. Okay, let's have a look at the concepts now. Let's have a look at the concepts. The concepts, they are as follows. I want you to remember that fundamental software concepts, they are abstraction, refinement, modularity. So this modularity now, that is the area centering to module. Software architecture, control hierarchy or program structure, structural partitioning, data structure, software procedure, then information hiding. You know this information hiding, I mentioned it in the module 1, that is first module. So the fundamental design concepts now, as I have mentioned, I will mention them again. Abstraction, but this time around now, let me make short explanation on each. I will make short explanation on each, that is each of the design concepts. Abstraction, this will allow designers to focus on solving a problem without being concerned about irrelevant lower level details. You know, I have discussed this abstraction in module 1. Then refinement. Here now, the designer will provide successively more detail, or let me say here now, successively more detail now will be provided by the designer for each design component. Refine, you know, refine, you are making something, let me say something pure. You are refining, you are making that thing pure. Then modularity here now, the software here will be broken to modules. That is the degree to which software can be understood by examining its components independently of one another. So here now, the software will be broken to modules or components, and each component will be examined to understand. Then software architecture. Here now, the overall structure of the software components and the ways in which that structure provides conceptual integrity for a system. So that is what we call software architecture. Then control hierarchy or program structure. That's number 5 of fundamental design concepts. Control hierarchy or program structure. This one represents the module organization and implies a control hierarchy. But it does not represent the procedural aspects of the software. So I want you to note that. Then structural partitioning. That's number 6. Horizontal partitioning defines 3 partitions: input, data transformation, and data output. That is, the data will be inputted. Let me use that word. The data will be transformed, and the data now will come out as output. Vertical partitioning. The one I said was a horizontal partitioning. That is, input data, transformation, and output. For vertical partitioning now, distributes control in a top-down manner. The control will be distributed in a top-down manner. That is, from the top to the base. Control decisions in top-level modules and processing work in lower-level modules. That is, the top will control decisions, the lower level will process work. Are you getting it now? Then data structure. So when we say data structure now, when we say structure, that is representation of the logical relationship among individual data. That is how the relationship will be represented logically among individual data elements. So this requires at least as much attention as algorithm design. So for data structure now, that's another course entirely. So you can go and check some things there. You understand now? Okay. Software procedure. We are still on fundamental design concepts. So software procedure is part. So when we say software procedure, this is just the precise specification of processing, the precise specification of processing. And when we say processing now, event sequences, decision points, repetitive operations, data organization or structure. Then the last one here is information ID. So I have mentioned this information ID in module 1 also. So when we say information now, that is data and procedure, contained within a module will be inaccessible to modules that have no need of such information. That is what we call information ID. So any information that is not needed by a particular module will not be accessible to that particular module. So if you are asked some questions now, maybe you are asked to list the steps in requirement analysis process. I think you'll be able to list them. Then let's say you are asked the fundamental design concepts that we just discussed now. You will be able to do so. And let's say you are asked the set of principles which have been established to help the software engineer in directing the design process. That is, the lay down principles that will enable the software engineer to obtain the best software project. So I think you'll be able to list and discuss them also. So we have come to the end of this unit now. So we want to have a look at Unit 3. We want to have a look at Unit 3. So under this Unit 3 now, we have what is called modularity. I've been saying it. Modularity here now, that is breaking of the software to modules. Are you getting it now? So here now, we are going to have a look at definition of modularity. We are going to differentiate between logical and physical modularity. We are going to discuss the benefits of modular design, that is, the benefit of employing modular design in software development. We are going to explain approaches of writing modular program and more that we are going to consider under this unit. So let's proceed now. So when we say modularity now, modularity here now is just separation and recombination of broken parts. Are you getting it now? Broken part, that is, the software project will not be one as whole. It will be broken to components. Are you getting it now? It will be broken to components. So as I've said now, modularity is a general system concept, which is the degree to which a system's components may be separated and recombined. That is, separation and recombination of system components. Are you getting it now? So it also refers to both the tightness and coupling between components. That is, how components, how they are, how tight to each other they are. You understand now? That is, the coupling of the components, the coupling together of the components, how tight they are, and the degree to which the rules of the system architecture enable or prohibit the mixing and matching of components. Are you getting it now? How the rule of the system architecture now, how it will enable or how it will prohibit the mixing and matching of components. So all these are called modularity. They are called modularity. So we want to have a look at modularity in category. Modularity in category. That is, we can categorize modularity as logical or physical. Modularity can be categorized as logical or physical. So let's have a look at logical modularity. When we say logical modularity, is concerned with the internal organization of code into logically related units. Are you getting it now? In modern high-level languages, logical modularity usually starts with the class, the smallest code group that can be defined. So I think you get the meaning of logical modularity now. Your module should expose its functionality as simple interfaces that shield colors. So the word shield here now, that is that let me say that cover colors from all implementation details. The functionality of a module should be accessible through a public interface that allows the module to expose its functionalities to the outside world while hiding its implementation details. That is why, let's say you are using what's it called? The now CBT exam software now. You are using it for the exam. You know, as a user now, the questions will be accessible to you together with the options. Then the correct option, that is the answers, will not be accessible to the user. And the correct answers, they are already contained in the software, but it will not be accessible to the user. Are you getting it now? So that is the part of work modularity does in software projects. Are you getting it now? Then let's have a look at a physical modularity. When you say physical modularity now, is probably the earliest form of modularity introduced in software creation. Physical modularity consists of two main components, and they are a file that contains compiled code and other resources, and two, an executing environment that understands how to execute the file. So for physical modularity now, is made up of two components, which are a file that contains compiled code and other resources, and two, an executing environment that understands how to execute the file. Are you getting it now? So we want to have a look at benefits of modular design, that is, advantages of modular design. Scalable development, that's number one. Testable code units, building robust system. When we say robust here, strong, that is building strong system. Easier modification and maintenance. When there is modular design, when modular design is employed in software projects, then it will be easy to modify and it will be easy to maintain. Are you getting it now? Okay. Then functionalist cable is also one of the benefits of modular design. So let's move to approaches now of writing modular programs. That is, programs in modules. Programs in modules. That's what we call modular programs. So let's consider the approaches now of writing modular programs. We have three basic approaches of designing modular programs, and they are: one, process-oriented design. Process-oriented design. For process-oriented design now, it places emphasis on the process with the objective being to design modules that have high cohesion and low coupling. Data flow analysis and data flow diagrams are often employed. So I want to explain the meaning of high cohesion. When we say cohesion in physics, it has to do with between the same particles. Between the same particles. So when we say high cohesion now, that is strong relationship between software elements or software components of the same module. Then, and low coupling. Coupling. When we are saying coupling now, it's like couple. You know, when we say couple, it has to do with more than one person. So low coupling now, that is more than more than one module. Are you getting it now? So there will be high cohesion among the elements, that is software elements of the same module, and low coupling between two or more modules. Are you getting it now? Then data oriented design. So for data oriented design now, this approach, the data comes first. The data will come first. That is, the structure of the data is determined first, and then procedures are designed in a way to fit to the structure of the data. Then object-oriented, that is object-oriented design. In this approach, the objective is to first identify the objects and then build the product around them. Build the product around them. The objects will be firstly identified, then the product will now be built around them. Are you getting it now? So in concentrate now, this technique is both data and process oriented. So this object oriented design is like combining or containing data oriented design and process oriented design. So I think you have gotten it now. So let's go to criteria for using modular design. Criteria for using modular design. Number one, modular decomposability. Modular decomposability, or let me say the reasons why we use modular design. Modular decomposability, that's number one. If the design method provides a systematic means for breaking problem into sub-problems, it will reduce the complexity of the overall problem, thereby achieving a modular solution. So the problem now is complex, and the problem now is now broken to components Then the complexity now of the problem will become reduced. Then modular composability. Modular composability. If the design method enables existing design components to be assembled into a new system, it will yield a modular solution that does not reinvent the wheel. Let's say there is, or let me say, there are already design components that will be joined together, that will be assembled into a new system. Then modular composability now will bring the solution. So the developer will not reinvent the wheel. That is, the developer will not be wasting time going back. Then number 3, modular understandability. So if a module now can be understood as a standalone unit without reference to other modules, it will be easy to build and easier to change. Are you getting it now? Then modular continuity. If small changes to the system component, if small changes to the system requirements result in changes to individual modules rather than system-wide changes, the impact of change-induced side effects will be minimized. That is, the modular continuity will be easy. Modular protection now. If an abnormal condition occurs within a module and its effects are constrained within that module, then impact of error-induced side effects are minimized. That is, if a particular error now or an abnormal condition now occurs within a module and the effect of that error, the effects produced by that error now are constrained or are restricted within that module, then there will be less or no impact. There will be less or no impact on other modules. I think you have gotten the reasons why we employ modular design during the design phase of software projects. So we want to have a look at attributes of a good module. For a good module now, it must be functionally independent. It must be cohesive. Let me take it one by one. For a good module now, the following attributes must be present. 1. Functional independence. Functional independence. Here now, modules will have high cohesion and low coupling. You know, when the cohesion now, as I've said, the software interrelationship among a particular module now is high. That relationship now is high. That is what we call high cohesion. Then the coupling, that is relationship between one module and the other, is low. Then the functions of each module will be independent. That is, one module will not need to depend on another module before it can perform its own function. Cohesion, I have discussed that one before. Cohesion, that is qualitative indication of the degree to which a module focuses on just one thing. on just one thing. That is, the module will not go and focus on another function belonging to another module, or the module will concentrate focusing on a particular function. On a particular function. Are you getting it now? Then coupling. Qualitative indication of the degree to which a module is connected. That is related to other modules and to the outside world. So that is what we call coupling. So a good module must possess the three attributes. 1. Functional independence, cohesion, and coupling. So I think you can explain the meanings of the three if you are asked to explain. If you are asked to explain functional independence, cohesion, and coupling, I believe you'll be able to do so. So let's have a look at steps to creating effective module. The steps now. Number 1 is to evaluate the first iteration of the program structure. I think I've explained what is called iteration before. Iteration, repetition. Evaluate the first iteration of the program structure to reduce coupling and improve cohesion. To reduce coupling and improve cohesion. To reduce coupling here now, to reduce the relationship between two or more modules. To improve cohesion here, to improve the focus on unique thing by a module. That is, a module focusing on a unique thing or on a unique function. So the other step is an exploded module becomes two or more modules in the final program structure. So when we say a module explodes, when we say it explodes, it means that the module becomes two or more modules in the final program structure. Then 3. An imploded module is the result of combining the processing implied by two or more modules. So an imploded module now is the result of combining the process implied by two or more modules. That is, the process implied by two or more modules now. The processing now is now combined into one. Or let me say, the process involved by two or more modules now is now combined. Are you getting it now? The process is now combined. Then, when the process combines now, when it combines, then it results in an imploded module. Are you getting it now? So, summarily now, an exploded module normally results when common processing exists in two or more modules and can be redefined as a separate cohesive module. When high coupling is expected, modules can sometimes be imploded to reduce passage of control, reference to global data, and interface complexity. Are you getting it now? So far now, we are on steps to creating effective module. Don't forget, we want to look at this one now. Attempt to minimize structures with high fan out. Strive for fanning as structure depth increases. Then keep the scope of a module. Keep the scope of a module within the scope of control for that module. I think you are getting the steps to creating an effective module. Then the scope of effect of a module is defined as all other modules that are affected by a decision made by that module. Then try to evaluate module interfaces to reduce complexity, to reduce redundancy, and to improve consistency. So those are some of steps to creating effective module. I think you have gotten it now. So we want to have a look at programming language that formally support module concepts. That is, some programming languages that formally support module concepts. They include IBM 360 assembler, COBOL, RPG, ADA, D, F, Fortran, Haskell, Pascal, Python, and so on and so forth. So let's have a look at module interconnection languages, MIL. MIL provides formal grammar constructs for deciding the various module interconnection to determine for deciding, MIL now we provide formal grammar constructs that will decide the various module interconnection specifications required to assemble a complete software system. Are you getting it now? So when you are coding a module, you are representing it small while assembling a system with the help of a module interconnection languages representing or is representing programming in the large. Are you getting it now? Let me come again. When you are coding a module, it represents programming in the small. But when you are assembling a system with the help of module interconnection languages, then you are programming in the large. So are you getting it now? So let's have a look at top-down design. When we say top-down design is a programming style, the core of traditional procedural languages, in which design begins by specifying complex pieces and then dividing them into successively smaller pieces. That is, you specify a complex pieces, then you now divide them into successively smaller pieces. Are you getting it now? So the method of writing a program using a top-down approach is to write a main procedure that names all the major functions it will read. So I want you to note that sentence. The sentence is, the method of writing a program using top-down approach is to write a main procedure that names all the major functions it will need. Are you getting it now? Okay. So we want to have a look at merits of top-down programming. Number one, separating the low-level work from the higher-level abstractions will lead to a modular design. 2. Modular design means development can be self-contained. 3. Having skeleton code illustrates clearly how low, that is, how low-level modules integrate. Then fewer operations errors, that is, the operation errors are few and others. So, and other merits. But we want to have a look at bottom up now. We have considered top down. We want to have a look at a bottom up approach. So in a bottom up approach now, the individual base elements of the system are first specified in great detail. Then these elements now are then connected together to form bigger subsystems, which are linked sometimes in many levels. That is, the bigger subsystems are linked in many levels until a complete top-level system is formed. So let me tell you one thing. This strategy now often resembles a seed model, whereby the beginnings are small, but eventually grow in complexity and completeness. It's like you plant a seed. Let's say a seed of iroko tree. You plant it. You know it is going to start from the beginning, and the beginning is small. Later it will grow and grow to become a big tree. Are you getting it now? Okay. So bottom up approach has one disadvantage. It has one setback. Let me tell you the setback now. We need to use a lot of perception to decide the functionality that is to be provided by the module. This approach is more suitable if a system is to be developed from existing system, because it starts from something else. So it starts from some existing modules. Modern software design approaches usually mix both top-down and bottom-up approaches. So when we talk of the modern software design now, that is the approaches now to the design. For modern software, it uses both top-down and bottom-up approaches. So with this now, we can conclude this unit. So far, we have dealt with design phase. We have dealt with modularity. We have dealt with benefits of modularity, types of modularity, logical and physical. Then we have dealt with approaches of writing modular program. Program here means software. I think you get it. Then we have considered the criteria for using modular design. The attributes of a good module. I want you to note that. The attributes are functional independence, cohesion, and coupling. We have considered programming languages that are used, that is, the programming languages that support module concepts. So we have considered the MIL, module interconnection languages. We have considered, let me give you example of module interconnection languages. You know, I gave you examples of programming languages that formally support module concepts. So let me give you programming languages now that support module interconnection. So the programming languages are called module interconnection languages. Module interconnection languages. So an example of module interconnection language is MIL75. MIL75. So I want you to note that. MIL75. So that's all about modularity. So we want to have a look at unit 4. So for this unit 4 now, pseudocode. Pseudocode. So when we say pseudocode now, it's a non-formal language. It's a way to create a logical structure. It's a way to describe actions which will be executed by the application. So using pseudocode now, the developer shows the application logic using its local language without applying the structural rules of a specific programming language. Are you getting it now? The advantage of using pseudocode is that the application logic can be easily comprehended, that is, can be easily understood by any developer in the development team. Moreover, when the application algorithm is expressed in pseudocode, it is very easy to convert the pseudocode into real code using any programming languages. So when you want to write lines of code for a particular software project, it is helpful, let me say it, it is helpful to start with a pseudocode. You understand now? So the pseudocode now will be converted to the actual programming language you want to use. Are you getting it now? So let's have a look at the guidelines for writing pseudocode, because not that you just write pseudocode anyhow. There are laid down guidelines. Some of them are: 1. Mimic good code and good English. 2. Ignore unnecessary details. 3. Don't belabor the obvious. That is, no need of belaboring the obvious. You take advantage of programming shorthands. That's number 4. Then 5, consider the context. 6, don't lose sight of the underlying model. Then you check for balance. So let me give short explanations on each of the guidelines for writing pseudocode. Number 1, as I said, you mimic code and good English. So here now, you will use aspects of both systems and you use both aspects of system means. Then this will make you to adhere to the style rules of both to some degree. When you are using aspects of both systems, then it will be means to adhering to the system rules of both to some degree. So the both here now, that is both systems. Do you get it now? You ignore unnecessary details. So if you are trying to write pseudocode, and if you are worrying about the placement of commas, or you are using too much detail, then it is good, or let me say it is a good idea to use some convention to group statements. Are you getting it now? For instance, begin, stroke end, brackets, or whatever else is clear. But what you must note is that you shouldn't be obsessed about syntax. You should not be obsessed. You should not be worried about syntax. When we are talking of syntax here now, that is structure of that language. Maybe you are using English language, so the structure, don't worry much about the structure. Are you getting it now? Then don't be labor the obvious. You know, in many cases now, the type of variable is clear from the context, unless it is critical that it is specified to be an integer or real. That is, to be a number that is an integer or a number that is real. So it is often unnecessary to make it explicit. It's not necessary to make it explicit. Then 4, you take advantage of programming shorthands using if, then, else, or looping structures. Are you getting it now? It's more concise than writing out the equivalent in English. So there's no need of writing the equivalent now in English. So you can just use the shorthands. If, then, else, or, and so on and so forth. Then you consider the context. If you are writing an algorithm for quick sort, the statement use quick sort to sort the values. When we say sort here now, that is to look out. We say to sort out something. Do you get it now? So to sort the values is hiding too much detail. So the statement use quick sort to sort the values. Is hiding too much detail. You getting it now? So don't lose sight of the underlying model. Don't lose sight of the underlying model. It should be possible here now to see through. That is, to see through your pseudocode to the model below. If not, that is, you are not able to analyze the algorithm easily. You are not able to analyze the algorithm easily. Then it is written at too high a level. Are you getting it now? Then you check for balance. So if the pseudocode is hard for a person to read or difficult to translate, that is, the pseudocode you have written is hard to translate or to read, then you know that something has been wrong. That is, something must be eventually wrong with the level of detail you have chosen to use. So if somebody cannot understand or translate your pseudocode, then the detail you have chosen to use, something have been eventually wrong with it. So let me take you to examples of pseudocode now. For instance now, you want to calculate sales value added tax, VAT. Then pseudocode the task. Pseudocode the task of doing the calculation for the final price of an item after figuring in sales tax. So I want you to note the three types of instructions. The three types of instructions here. So input will means get. Input will mean get. Process or calculate. Then output will mean display. Are you getting it now? So here is the pseudocode description now. Line 1, get price of item. Line 2, get VAT rate. Line 3, VAT equals to price of times time VAT rate. Line 3, VAT equals to price of item times VAT rate. That is line 3. That is VAT equals to price of items times VAT rate. Then line 4, final price equals to price of item plus VAT. Then line 5, display final price. Line 6, stop. So for that line 6 stop now, the execution of the program will stop when it gets to line 6 instruction. So I think you can get the example of a pseudocode now. So it is this pseudocode now that will be transformed to real HLL, that is high level language, needed to write the codes of that particular system software project. So that's all about pseudo code now. So what's there is that we are going to have a look at programming environment, case tools and hippo diagram. Programming environment, case tools and hippo diagram. So what is the meaning of programming environment? When we say programming environment, programming environment, that's environment. What's the meaning? Programming environments give basic tools and application programming interfaces, that is APIs, application programming interfaces, APIs or APIs. Put it like that, APIs, 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 application programming interfaces, necessary to construct programs. Programming environments help the creation, modification, execution and debugging of programs. The goal of integrating a programming environment is more than simply building tools that share a common database and provide a consistent user interface. So when we say programming environment now, programming environment is a software on its own. It's a software on its own. So that is why we call it programming software. It's a software on its own that the developer, the software developer will now be able to get all the tools he needs to develop the project. So he is going to get all the tools from programming environment. Are you getting it now? So for this programming environment now, it has history. So let me just introduce the history to you, students. The history of software tools began with the first computers in the early 1950s that used linkers, loaders, and control programs. In the early 1970s, the tools became famous with Unix, with tools like grep, awk, and make that were meant to be combined. Make that to be combined flexibly with pipes. So are you getting it now? So the term software tools now came from the book of the same name by Brian Kemigan and P.J. Plugger. Are you getting it now? So as some tools now, they have been maintained, that is, as some tools have been maintained, they have been integrated into more powerful integrated development environment. So this issue of programming environment now in the modern technology has become IDEs, that is integrated development environments. Are you getting it now? So these environments now we combine functionality into one place. It will combine functionality into one place. So let me have a look at types of programming environments we have. So for software development tools, the software development tools now, roughly, we can divide them into the following categories. performance analysis tools, debugging tools, static analysis and formal verification tools, then correctness checking tools, application beauties, then IDE. So this IDE now is the major concern, Are you getting it now? Okay. So as I said, let me give examples of IDEs, that is integrated development environments. DeFi, Microsoft Visual Studio, that one is a common example. You can get it from the software vendors. Then Eclipse, NetBeans, Lazarus, and many others. So let's have a look at case tools. I've mentioned case before. I've mentioned it in the first module. Case tools are a class of software that automates. They are going to automate many of the activities involved in various life cycle phases. Okay, for instance, when establishing the functional requirements of a proposed application, prototyping tools can be used to develop graphic models of application screens to assist end users to visualize how an application will look after development. So, prototyping tools now, they can be used for that function. Do you get it now? So, study more on the case tools. Then, let me give some types of case tools. Some types of case tools are data modeling tools, configuration management tools, model transformation tools, program transformation tools, refactoring tools, unified modeling language. So that's just some types of case tools. Are you getting it now? So for these case tools now, you study more about it. Then when we say case environment, an environment is a collection of case tools and workbenches that support the software process. Case environments are classified based on the focus of integration as 1. Toolkits, language-centered, integrated, 4th generation, process-centered, and so on. So for the various categories now, toolkits, language-centered, integrated, and so on. Let us have a look at the explanation now. For toolkits now, they are loosely integrated collections of products, easily extended by aggregating different tools and workbenches. Then for language-centered now, the environment itself is written in the programming language for which it was developed. So it becomes language-centered environment. Then integrated now, this environment achieves presentation integration by providing uniform, consistent, and coherent tool and workbench interfaces. So 4th generation now, when we say 4th generation environment, they were the first integrated environment. They are sets of tools and workbenches supporting the deployment of a specific class of programs. You know, tools and workbenches, they are repeatedly mentioned here. It can be likened to a carpenter. You know, a carpenter or a furniture maker now, we have what is called a workbench. The bench will be built in form of a table. The clamp will be there. So if the furniture maker want to saw a plank, the plank will be clamped to the workbench. Then the furniture maker now can now use a saw to saw the plank. So the saw, the hammer, the jack plane, the pinch, the what's it called, the maybe the mallet and other tools now, they are called the tools. You understand now? They are called what? The tools, or let me say they are likened to tools in the software parlance, that is in the software language. Then the workbench now, that is the bench on which the furniture maker or the carpenter will be doing his work. So I think you have gotten it now. So let's see the application areas of case tools. The applications areas of case tools now: modeling business, real world process and data flow, development of data models in the form of entity relationship program, development of process and functions descriptions, production of database creation, SQL and stored procedures. So have you gotten the application areas now? Then it has risk, case risk. So we have some risks that are associated with a case. Number one, inadequate standardization. So if we are linking case tools from different vendors, let's say design tool from company X, programming tool from company Y, then it may be difficult if the product do not use standardized code. That is, the product, they don't use the standardized code structures. Are you getting it? And data classifications. File formats can be converted, but usually not economically. So I think you can get the risk now. Then the second risk, unrealistic expectations. Unrealistic expectations. So organizations often implement case technologies to reduce development costs. Implementing case strategies usually involves high startup cost. So the cost will be high. Then quick implementation, that is quick implementation. So when we are implementing case technologies, then it can involve a significant change from traditional development environments. So typically, organizations should not use case tools the first time on critical projects or projects with short deadline. So when we are considering critical projects, especially medical projects, that is software used in medical environments, then software used in military operations. So case tools must not be used at first time. They must not be used at first time. You understand now? Then weak repository controls. That's another risk of using case tools. Weak repository controls. Failure to adequately control access to case repositories. When you say case repositories now, we are talking of resource location of case tools, where case tools where they are resourcefully packed. Are you getting it now? So failure to adequately control access to case repositories may result in security breaches or damage to the work documents, system design, or code module stored in the repository. So it can cause damage to the work documents, to the system designs, or to the code modules stored in the repository, that is, in that particular repository where the case tools reside. Do you get it now? So controls include protecting the repositories with appropriate access, version, and backup control. So if you want to control the risk now, then we can protect the repositories with appropriate access. That is, access to the repository will be controlled, will be restricted, will be regulated. Are you getting it now? Then version and backup controls can also be enabled. So I think you have gotten the risk associated with case, that is, with case environment. Now we come to the end of the module now. Let's have a look at HIPPO diagrams, HIPO. So the acronym HIPPO stands for hierarchy plus input process output. So HIPPO is a technique, that is a tool for planning or documenting a computer program. So a HIPPO model consists of a hierarchy chart that graphically represents the program's control structure and a set of HIPPO here now, IPO, input process output, that is HIPPO charts that describe the inputs to, the outputs from, and the function or processes performed by each module on the hierarchy chart. So you go to programming and algorithm, you understand better the meaning of HIPPO. Then data structure also, you can get some things there also. Okay, so let's proceed to strengths, weaknesses, and limitations. So when we talk of strengths and weaknesses and limitations now of HIPPO, that is hierarchy plus input process output. Using HIPPO technique, designers can evaluate and refine a program's design and correct errors prior to implementation. Given the graphic nature of HIPPO, users and managers can easily follow a program structure. The hierarchy chart serves as a useful planning and visualization document for managing the program development process. The HIPPO charts, HIPPO now, IPO, input process output charts defined for the programmer each module's input, that is, each input of the module, outputs, and algorithm. So you go and study this issue of HIPPO and HIPPO. Then let's have a look at a hierarchy chart. Then we consider a set of tasks to be performed by an interactive inventory program manage inventory. So these are the set of tasks now. Updating of stock, that is stock update, process sale, process return, process shipment, generate report, response to query, then record modification, record adding, and record deletion, and some others. So I think by now we come to the end of the module 3. We come to the end of module 3. So the course now remains one module. We come to the end of module 2. So it remains module 3. The course contains 3 modules. 3 modules. Not 4 modules, but 3 modules. Module 1, 2, and 3. So module 1 and 2 have been dealt with now. So it remains module 3. So meet me next class for the module 3 explanation. So I say goodbye.